Hot water hits your shoulders. Perfect temperature. Then the curtain peels off the wall. It wraps around your leg like it's grabbing you. You kick it away. It comes back. Every shower. Every time. For your whole life. You blamed the window, the fan, a draft sneaking under the door. You were wrong. And so was almost every scientist for the last 50 years. One curtain, one obsessed professor, and a law of physics running in your bathroom right now that you have never once noticed. Questions that sound simple and turn out not to be are the whole business of the smart side. Here's the question that actually matters. If it's not a draft, what has enough force to move wet plastic toward you every single time, no matter the house, the window, the season? Nobody had a real answer until a guy named David Schmidt got sick of his own shower curtain. Schmidt taught fluid dynamics at UMass Amherst. Not a hobbyist, not a blogger. The kind of engineer who normally spends his career on jet turbines. In the early 2000s, he got annoyed enough at his own bathroom that he built a full computer simulation of a shower. Water spray, curtain, air, all of it, just to catch the air in the act. Before Schmidt, the accepted answer wasn't even the draft theory. It was Bernoulli's principle, the same rule that keeps a 747 in the sky. Fast-moving air creates lower pressure than slow-moving air. The shower blasts water fast through the space behind the curtain. That speeds up the air, pressure drops, curtain gets pulled in. Clean explanation. Textbooks loved it. It got repeated for decades. Schmidt's simulation blew it up. His model showed something nobody expected. A vortex. A small spinning column of air, lying on its side, sitting right there inside your shower while you're rinsing shampoo out of your hair. Falling water drags air straight down with it. That air slams into the tub floor, has nowhere left to go, and curls back on itself. That curling motion builds a rotating core of low pressure, right in the middle of the tub, right between you and the curtain. Spinning air always drops pressure at its center. That's not a bathroom quirk. That's the same rule behind a tornado's core, behind a hurricane's eye, behind the funnel that forms when you pull the plug on a full sink. Your shower is running a tiny, harmless version of the exact same trick. Here's the number that makes it real. Hurricane force winds start around 74 miles an hour. A strong tornado can spin past 200 at its core. Your shower vortex isn't dangerous. It's a soft little swirl you'd never feel on your skin. But the mechanism inside it is identical, just shrunk down from a supercell to the size of a bathtub. Schmidt published the finding in 2001 in an actual fluid dynamics journal, using software built for jet engines and race cars, aimed at a curtain that cost $2 at a drugstore. If a scientist modeling his own shower to fight back against a curtain is as good as I think it is, hit like right now. He didn't stop at the explanation. His single simulation, run in full, showed the vortex forming and holding strong for the whole 30 seconds of shower time it modeled. The vortex in place, steady, the whole way through. The vortex held its shape. What actually helped more, a curved shower rod, curtains weighted at the hem, hooks spaced wider apart so the fabric hangs loose instead of pulled taut into the airflow. None of that erases the vortex. It just gives the curtain enough slack and weight that the pull can't win. And here's the twist most people miss. This isn't only a shower thing. The same low-pressure core forms behind moving vehicles, which is why debris and even smaller cars can get tugged toward the back of a speeding truck. It's why a running train can pull a person standing too close to the platform edge. Same spinning air, same pressure drop, wildly different scale. So tomorrow, when it happens again, and it will, because physics doesn't take a day off, You're not standing in a drafty bathroom. You're standing inside a tiny weather system you built yourself, with a real low-pressure core, made entirely of falling water and moving air. The curtain isn't haunted. It isn't the window. It's a professor's laptop, a spinning column of air no wider than your bathtub, and one blunt universal law. Pressure differences move things, whether that thing is a 2,000-ton airliner or 40 cents of shower liner. It'll wrap your leg again tomorrow. Now you know exactly why.